Good morning, young people. It's Miss Rains. Today we're going to start talking a little bit more about solution stoichiometry, but this time we're talking about oxidation reduction reactions and how we go about balancing them. Now, a little secret, most reactions are redox reactions. Actually, almost all are. Almost all do a transfer of electrons, which is what is required when we have a reaction. But in a redox reaction, what ends up happening is there aren't equal numbers of electrons being transferred from one thing to another. We have an unequal transfer. And so what we can't do is we cannot balance it in the same way that we've balanced it before. So we have to learn a little bit more about this concept of oxidation reduction and become more familiar with it. So basically what happens is something has to gain electrons or become more negative, and something has to lose electrons or become more positive. So oxidation, substances are losing electrons, so they become more positive. And this is going to be really key to determining what's being oxidized and what's being reduced. If it becomes more positive, if it gets more positive, that's not if it gets positive, but if it gets more positive, then it's oxidized. Reduction is something that is gaining. So this is going to become more negative. So more negative means it's being reduced. That doesn't always mean that it's negative. It just means that it becomes more negative. Okay? And we'll show you examples of that in just a second. So oxidation. Oxidation is a loss of electrons. Atoms will increase charge when they're oxidized. Increasing charge means they become more positive. Okay? Sorry, I've got to erase that. I forgot that it was over here. Okay? Not sure why that's not erasing. Okay, reduction is a gaining of electrons. So atoms will decrease charge and they will become more negative. So while these become more positive, these become more negative. Okay, so how do we determine that? Well, we use some mnemonic devices. Leo says GER or oil rig. So losing electrons is oxidation. Leo, losing electrons, oxidation. Okay, and GER, gaining electrons, reduction. So think of a lion. Leo the lion, losing electrons is oxidation. What he makes, sounds he makes, GER, gaining electrons is reduction. The other one is oil rig. Oxidation is losing, O-I-L, oil. Reduction is gaining. So these are two tricks to remember that in your head. So how do we know oxidation states? And how do we determine what's gaining or losing? Well, we have to do these things called oxidation states or oxidation numbers. Now, some oxidation numbers we know or we have predicted before in the past, but there are going to be some things that are going to change. So we're going to learn some rules that are going to guide us in what we're going to be doing. So here's the first rule. An oxidation number is the assigned charge on an atom, just like in formula writing. So in formula writing, we write the formula and then we can actually assign a charge to each of those things. Typically, we've looked at the charges of the ions. But what happens when we have a polyatomic ion? That's a covalently bonded substance that is then forming a charge because it's missing an electron. So we're going to be looking at all of those. So rules for assigning oxidation numbers. The oxidation number of any atom or element is 0. So if it's a neutral atom, not an ion, it has a 0 oxidation number, and that includes all diatomic and allotropies. So like N2, P4, S8. P4 and S8 are allotropes of phosphorus and sulfur, just ways that they can come in crystalline form. N2 is a diatomic molecule, just like all the other Brinkelhoffs. Anytime you have an atom, an element, it is 0 charge. So silver, 0 charge. Iron, 0 charge. As long as it's not an ion, it has a 0 charge. The oxidation number of monatomic ion is the same as its charge. So these usually apply to mostly metals. We're usually talking about metals, but there are other ones that we're talking about. But typically, this is what we're talking about. If we have a single ion, we're talking about that. So in a compound's fluorine is always going to get a -1. This has to do with electronegativity. Fluorine is the most electronegative substance on the periodic table. It will always be assigned a number first, so fluorine is always going to be -1 because that's its typical state. Okay, we'll talk about that in an example that we see in a little bit. Oxygen is usually, notice it says the word usually, assigned a -2. And covalent compounds like CO, CO2, SO2, and SO3. The exception to this rule include peroxides, because in peroxides we have this group. And if we have this group, the oxygen can't have a -2. It has to have a -1 when it's in a peroxide. Okay, so OF2, the oxygen is assigned a +2, so the F is a -2. Okay, so those are the exceptions to the rule. If we have oxygen, typically it's a -2. Exceptions are peroxides and this very strange group that has this fluorine, this OF2, this oxygen difluoride. Okay, an oxygen difluoride here would have a +2 charge because fluorine gets a -1 before oxygen gets a -2 because it's more electronegative. Okay, in compounds with nonmetals, hydrogen is assigned a +1. So that means hydrogen is first, or hydrogen's part of a covalent bond. It's always going to be assigned a +1. But if we have a metal hydride, for example, oh, come on now, NaH, that's a hydride. That's going to be a -1 charge because the +1 is on the Na. So a couple of exceptions about the ones that we use all the time. We don't see these hydrides very often. Okay, the sum of the oxidation numbers must be 0 for anything that is a neutral compound, and for anything that is charged, the total sum of the oxidation numbers must equal the charge, either on the ion or on the group, whatever it is. So we just have to remember those rules. So let's see if we can apply those. So you have the rules in front of you. Exercise 15A, we have CO2. So we're looking here. We know that the oxygen is going to be a -2. So what we do, this is a neutral compound. We know that the total charge is 0. So we set everything equal to 0. We have 2 oxygens at a -2. And we have a carbon that we don't know the charge of. So x minus 4 is equal to 0. So x is equal to a +4. So that means that the carbon has a +4 charge. That's the oxidation state for carbon. Okay, let's try another one. Sorry, some things aren't coming up the way I thought they would. So SF6, once again, it's a compound, so it's going to equal to 0. Fluorine gets a -1 because it's the most electronegative. So 6 minus 1 plus x. So x plus 6 minus 1 is equal to 0. So x minus 6 is equal to 0. X is equal to a +6. So the sulfur has a +6 charge in SF6. All right, let's try another one. So here we have a polyatomic ion, so we're going to have something a little different. It's not equal to 0. Its total charge is equal to -1, so it has to be that. Oxygen, again, is a -2, so we have 3 times a -2 plus x. X is the n. So we have x minus 6 is equal to -1, so x is equal to a +5. So the nitrogen here takes on a +5 charge. One more, and this is one in which we have to look at nitrogen as the most electronegative of the 2 atoms here. Nitrogen is the most electronegative of the 2 atoms, so it is going to get its normal charge, its normal monoatomic ion charge. And if you know nitrogen is a nonmetal, it forms a -3 charge more easily, so nitrogen is going to be considered -3. Remember, the total charge on cyanide is a -1, so we have to say -1 is equal to everything. We have 1 nitrogen, so we have -3. We have a carbon, which we don't know. So x minus 3 is equal to -1. So x is equal to a +2. So in this case, the carbon is a +2 charged carbon. It's really that simple. It can get complicated, but if you remember the rules and you remember H and O are always assigned a -2 for O, a +1 for H, and then monatomic, especially the metals, are assigned their charge. And then if you remember about the most electronegative substance is always going to get its charge first before the other guy does. So in this case, nitrogen is more electronegative than carbon, therefore nitrogen gets its normal charge before carbon gets its normal charge. Okay? So here are some ones that you can try on your own. We already know that K is a +1 and O is a -2, so try to find what the M is. We know that the O is a -2 and the H is a +1, so try to find the C. In this case, this is not a metal hydride, this is a covalent bond, so H is a +1. I need you to find the P. We know here magnesium is going to be a +2, oxygen is going to be a -2, H is going to be a +1, so I want you to find the carbon. Be prepared to answer these on Wednesday in class. Some of you are taking the notes a little early, and that's fine, but be prepared to answer these Wednesday in class after we've finished our last lab. Okay, so you've seen the ones that I'm trying to get you to find. Carbon in this one, phosphorus in this one, carbon in this one, and the manganese in this one. Okay? All right, let's move forward. So we have to also remember, though, oxidation states can be a little strange. So if we look at this compound right here, oxygen is a -2, and this is a compound, so that means it's equal to 0. We have 4 times a -2 plus 3x. Why 3x? Because there are 3 iron. So we have to include that in our little formula here. We're just doing algebra. So we get 3x minus 8 is equal to 0. So 3x is equal to 8. So x is equal to 8/3. You're like, can we have that? And the answer is absolutely. Iron things can be halves, thirds, they can be fractions, so don't panic about that. Just make sure that you're doing the right rules. Okay, make sure you're doing the right rules. So, exercise 17. How does this apply to reactions? Well, here we have a chemical reaction. When powdered aluminum metal is mixed with pulverized iodine crystal in a drop of water, and it's added to a drop of water, and then the reaction gets started. The resulting reaction produces a great deal of energy. The mixture bursts into flames, and purple smoke of I2 vapor is produced from the excess iodine. The equation for the reaction is as follows. So we have aluminum and iodide makes this. Okay, for this reaction, identify the atoms that are oxidized and reduced. How are they oxidized and reduced? So to do this, we have to determine oxidation states. So first of all, we have aluminum as a solid. Well, that's an element. Aluminum as an element has a 0 charge. Iodine is a solid. What's I2? It's its diatomic form, so it's its elemental form. So it also has a 0 charge. Then we come over here and we look at this compound. We have AlI3. Well, that's easy. Al is a +3. I is a -1. So now we have all of the charges of our substance. What's happening? Al is going from a 0 to a +3. So Al is losing electrons. When you go from a 0 to a +3, you had to lose electrons to do that. So it is oxidized. So that means if we look at the iodine, I is going from a 0 to a -1. So I is gaining electrons because it's going from a 0 to a -1. It's getting more negative. Remember, this one got more positive, this one got more negative. So it is reduced. So we can determine if things are being reduced or if they're being oxidized by looking at the charges that we assign them. Okay? Next one. Metallurgy, the process of producing metal from its ore, always involves oxidation-reduction reactions. In the metallurgy of galena, that's lead sulfide, the principal lead-containing ore that we find, the first step in the conversion of lead sulfide to its oxide, is a process called roasting. So here's the roasting process. We see the balanced chemical equation for that. Then the oxide is treated with carbon monoxide to produce the free metal. So carbon monoxide is thrown in there, and it gives us the free lead and carbon dioxide. I didn't do that. Sorry about that. That's a mistake. Okay, so it says, for this reaction, identify the atoms that are oxidized and reduced for each reaction. Not for this. It should say for each. Sorry, I think on your paper it does say for each. Okay, so we're going here first. We have a +2 lead, a -2 sulfur. We have a 0 O. Okay, so we come over here. We have a +2 lead and a -2 O. We have another -2 O, but now we have sulfur that we don't know the charge of. So how do we figure that out? Well, it's equal to 0 because it's a compound. There are 2 oxygens with a -2 charge plus X. So X minus 4 is equal to 0. So X is equal to a +4. So S has a +4. Now I can see the leads are the same, so I'm just going to cancel the lead out for a minute. I don't need to look at the lead because it's not being oxidized or reduced. So now I'm looking at the oxygen. No, let's look at the sulfur. Sulfur's first. It goes from S2- to S4+. Yeah, it's getting more positive. So the sulfur is losing electrons, so it is oxidized. Okay, so it's going from a -2 to a +4. That's more positive. O is going from a 0 to a -2. So O is gaining electrons. It's getting more negative. So it is reduced. Sorry, I'm still learning how to write on my little tablet here. It's better than with my finger, though. So in the first one, sulfur is losing electrons, so it's oxidized. O is gaining electrons, so it's reduced. Now let's look at the second reaction. We have Pb with a 2+ charge, O with a 2- charge. We have O with a 2- charge, which means the C, in this case, remember, 0 is equal to -2 and X, so X is equal to a +2. So we have a +2C. We have a 0 Pb. We have a -2 O, and this time this O is there are 2 of them, so 2 times a -2 plus an X. X minus 4 is equal to 0, so X is equal to a +4. So this C is a +4. What thing's not changing? Yeah, the O is not changing, so I'm not going to look at the O. I'm going to ignore the O. Okay? And all of them. O is not changing. So I start with the Pb. The Pb is going from a 2+ to a 0. What's happening to the Pb? It's going from a 2+ to a 0 charge. So Pb is gaining electrons. It's getting more negative. It's getting more negative, so it is reduced. Okay, so then we look at the C. The C is going from a 2 to a +4, a +2 to a +4. So C is going from a +2 to a +4. It's getting more positive, so C is losing electrons. So it is oxidized. It's really that simple, ladies and gentlemen. We just have to assign charges, and then we have to figure those things out. So this will be a good stopping point for you if you don't have time to continue watching, and then come back at this point after having practiced a couple problems and thought about it a little bit. The next portion is going to be balancing these redox reactions so we can get balanced reactions. All right. So balancing redox reactions, the HAP method reaction. Basically, we're going to divide these things into 2 reactions. We're going to do an oxidation half and a reduction half. Okay? We're going to use all the substances, all the elements that are oxidized and put them in one reaction, all the things that are reduced and put them in another reaction, and we're going to balance all of those. So then we start off by balancing any element except for hydrogen and oxygen. This besides is really important. We're going to use a different method to balance hydrogen and oxygen. So if there's hydrogen and oxygen anywhere in there, don't panic. Balance all the other elements first. Then step 3 is to balance the O's by adding water on the opposite side of the O. Once you get the O's balanced, then we balance H's by adding H+ on the opposite side of the H's. Then we have to look at the charge. So we have to look at how many electrons were being lost or gained from side to side. And we have to add the electrons to the side that they're missing from. So if we're oxidized, that means we've lost electrons. That means the reactant side has more electrons than the product side. So we're going to be adding the electrons for oxidation on the product side. For a reduction reaction, there are fewer on the reactant side than the product side. We have more electrons on the product side. So we're going to be adding electrons over here. Okay? So when we think about what's happening, we can see that that's what we're going to do. The oxidation reaction is going to get electrons on the product side. The reduction reaction is going to get electrons on the reactant side, because I end up in the product side with more electrons than I started with. On the oxidized side, I end up with fewer electrons on the product side than I started with. After I've done that, I have to make sure that the number of electrons on each half reaction is the same, because they must cancel out. They must cancel out if they are not the same. So if these two numbers on the other side of the arrow are not the same, then I have to multiply each half reaction by a whole number to make them cancel out. You'll see examples of this. Don't panic. Then I'm going to add the two reactions back together, canceling out anything that is common from one side to the other. If I have more than something, I cancel out what goes away on one side and I keep whatever I need to keep on the other side. All right? So if we're in basic situation, and we'll do this a little bit later and practice this, we neutralize any H plus by adding OH minus on the opposite side, and then make sure that everything's balanced. So we'll be doing number 8 a little bit later. Okay. Number 9 is check. What do you need to check? You need to check charge. So the charge must be equal on each side, and you need to check numbers of atoms. The law of conservation of mass still applies. And that's also the law of conservation of charge. We have to make sure both are the same. So when we do these, we have to double check that. All right, so the next step. Let's look at a sample problem. So assign the oxidation numbers and balance this equation. And notice it says it's acidic, which means we really don't have to worry about what we're doing because we do it in the acidic reaction anyway. So we know that this is a -2, and because this is permanganate, we know a -1 is equal to 4 times a -2 plus x. X minus 8 is equal to -1, so x is equal to +7. So the manganese is a +7. Fe already has a charge, it's a +2. We already know that. This one has a +2, and this one has a +3. Pretty easy there, huh? So now we see that manganese is going from a 7 to a 2. Manganese is your reduction reaction. So let me erase some stuff here. Sorry, I need to erase a couple things so I have more room. I should have done this work up at the top. Okay, so my reduction reaction is MnO4 minus yields Mn2 plus. That's my reduction half reaction. Okay, my oxidation half reaction I'm going to put over here, and it's Fe2 plus yields Fe3 plus. So let's start with the permanganate. The permanganate, I have oxygens. I have 2 manganese, so they're good. But I have 4 oxygens, so I have to add 4 water over here. But adding water, I added hydrogen, so now I have 8 hydrogen that I have to add over here. Okay, 8 hydrogen are going over here. And remember, I started out at a +7 here, and I have a +2 here, so I have 5 more electrons on this side than I do this side. So I have to add 5 electrons here. That's the difference between a +7 minus a +2. It's a +5. So there are 5 more electrons on the product side than on the reactant side. So I put the electrons for the reduction reaction on the reactant side. So that is now balanced. Everything is balanced. This one is simple. I don't have anything except Fe. Fe is already balanced. Now I need to look at the charge. I have a +2 and a +3. This guy has 1 fewer electron. So I add 1 electron over here. My problem is I have 5 electrons here and 1 electron here. So this reaction has to be multiplied by 5 to make the electrons equal. So I'm going to rewrite it over here after multiplying. 5 Fe 2 plus yields 5 Fe 3 plus 5 electrons. So you'll notice now I'm going to add the 2 reactions back together. The electrons go away. Nothing else cancels out. So I write 8H plus MnO4 minus aqueous. By the way, all of this stuff is aqueous if it's an ion. And that will give us Mn2 plus aqueous. Sorry, I keep pressing that little button. Plus 5 Fe3 plus aqueous plus 4 H2O. So now we check. So I have 8 hydrogen over here. I have 8 hydrogen over here. I have 4 oxygen, 1 manganese, 1 manganese. 4 oxygen, 4 oxygen. 5 iron, 5 iron. So that's all good. I have 8 positive here, plus a 1 negative here, plus a 10 positive here. So that's a total of 17 positive charge. On this side I have a 2 positive, plus 5 times a 3 positive, that's a 15 positive, plus 0, because there's no charge there. That's a plus 17 as well. So now our charges are the same, our numbers are the same, so this is the balanced equation right there. Yeah, it's more complicated, I agree. But there are cases where you can't balance it any other way. And this is the best way to get it balanced. And so when you have that reaction that they're not giving away equal numbers of electrons to each other, then you have to use this kind of balancing. This is an example of that. Let's try another sample problem. Oh, really great, because we have permanganate again. So we already know that that's a -2 and that's a +7. We already know that the I is a -1, so that's really good. We know the Mn is a +2, and we get I2. Hey, I2 is elemental, so it's 0. All right, so we already know that the permanganate is the reduced guy. It doesn't really matter which side you write reduced and oxidized on. It really doesn't, as long as you separate them. The whole point here is that we're separating them, not that we're, trying to do anything crazy. All right, so we already know what to do here. The manganese are okay. We have to go over here and add 4 water. This one is going to be the exact same half reaction as we just did on the other problem, because it's exactly the same. It's exactly the same half reaction. So it gets the same thing. So we have 5 electrons there. Now, here we have 2 iodine and we only have 1. So we have to add a 2. That means that we have double the number of electrons that are going somewhere. So we have 2 electrons over here, but we have no electrons over here, so we need 2 electrons over here. So when we do that, what we end up with is a situation where things are not exactly the same. So we can see we have 5 electrons here and 2 electrons here. So this side is going to have to be multiplied by 5, and this side is going to have to be multiplied by 2 to get them to even out. So when we do that, we get 8H plus, no, I'm sorry, not 8H plus, 16H plus 2 MnO4 minus plus 10 electrons yields 2 Mn2 plus 8 water molecules. And over here we get 10 10 iodine. Sorry, I keep forgetting to multiply. Yielding 5 I2 gas plus 10 electrons. So now the electrons cancel out, nothing else does, so now we write what we see. We add these two together. We get 16H plus 2MnO4 minus plus 10I minus yields 2Mn2 plus 5I2 plus 8H2O liquid. So we double check everything. I have 16 hydrogens. I have 16 hydrogens. I have 2 manganese. I have 2 manganese. I have 8 oxygens. I have 8 oxygens. I have 10 iodine. I have 10 iodine. So as numbers, they're correct. So now let's check the charge. I have 16 plus. I have 2 minus. And I have 10 minus. So that means I have an overall charge of 4 plus there. Okay, so I have a 4 plus a 0 plus a 0. So it's a 4 plus. So now we know the charges are equal, so now we know that that's balanced. That's always a double check. It's pretty quick. It's pretty simple. It follows the law of conservation of matter, and it helps us out. So let's look at a couple more problems. Here, potassium dichromate is a bright orange compound that can be reduced to a blue-violet solution of chromium ions under certain conditions. Potassium dichromate reacts with ethyl alcohol as shown below. Use the balance this equation using the half reaction method. So let me tell you something really quickly. I'm not going to worry about this guy right here or this guy right here, because when we balance, we're going to get those guys back in. I'm not going to worry about them. I'm going to worry about what I see right here. I know that O's are 2 minuses, H's are 1 plus. So I'm going to put those in. Now I've got to figure out, I already know the CR here is a 3 plus. So what's the CR here? Well, I have a minus 2 is equal to 14 times a minus 2 plus 2x. Remember there are 2 chromiums, so 2x minus, no, not 14, sorry, that's 7. So it would be minus 14 is equal to a negative 2. So 2x is equal to a positive 12. That means x is equal to a positive 6. So this chromium is a plus 6. The carbon here, this is a little more complicated, but nonetheless we can do it. 0 is equal to, we have 1, 2 minus, plus 6, 1 plus 2x. Okay, so we have 2x plus 6 minus 2 is equal to 0. So 2x is equal to a negative 4. X is equal to a negative 2. So we have a negative 2 carbon there. How about the carbon in the CO2? We've already done this one before, haven't we? 0 is equal to 2 times a negative 2. And see, when you start repeating them often, you will start remembering some of these, okay? So, I'm sorry, 0. So x is equal to negative 4. I keep getting ahead of myself. So x is equal to negative 4. So if I look at the chromium, I'm going from a plus 6 to a plus 3. Yeah, that's the reduction. So let's go ahead and do that. The dichromate is the reduction reaction. Okay, the ethanol going to carbon dioxide is the, I'm sorry, this should be a plus, not a minus, is the oxidation reaction because it's going from a minus 2 to a plus 4. So I put C2H5OH going to CO2. And you're saying, Ms. Rains, what about the H and the H2O? Again, it will come back into play. Do not panic. Do not throw a fit. Do not go crazy. Just trust me when I say you will find H pluses and OHs when you get finished. Don't play. Don't panic. Don't do anything crazy. Okay, so let's go to the chromium first. We see we have 2 chromiums, so we have to put a 2 right there. That means that this chromium is got a 6 plus charge, and this chromium has a 3 plus. Each are gaining 3 electrons. There are 2 of them, so they're gaining 6 electrons. So this side has 6 more electrons than this. So I put 6 electrons right there. Okay? Now, I'm sorry. I did that so backwards. I shouldn't be worried about the electrons just yet. So let me try that again. Forget that I said that. So let's go. We've got chromiums. All right. So confused right now. It's Saturday morning. All right, so let's look at the O. So we have 7O. So that means I have to add 7 water molecules. Look, there's my water. Okay, because I had to add 7 water molecules over here, I have to add 14 H plus over here. So now I have the oxygens and the hydrogens all balanced. Now let's go back to the electrons. We already know it's 6 electrons because each chromium is gaining 3 electrons from reactant side to product side. So that we have to add 6 electrons on the reactant side to make sure it's equal because we have 2 chromiums doing that. Okay, so we come to this side. On this side we see we have 2 C's and 1 C, so we have to add a 2 here. Now we have 4 O's on this side, but only 1 on this side. So that means we have to add 3 waters. 3 waters. Now I have 6 H's right there, plus another 6. So that means I have to add 12 H pluses on this side. Now we have to figure out the charge. I'm going from a 2 minus to a 4 plus. That's 6 electrons. 6 electrons are lost in this reaction. So that means the reactant side has 6 more electrons for each carbon than this side. That means that this one has 12 electrons that it needs on the product side. Because each carbon is losing 6, I need 12 because there are 2 carbons. So I look at my electron charge. I've got 12 and I've got 6. That means I've got to multiply this equation by 2. So I get 28 H plus 2 dichromate ions plus 12 electrons yields 4 chromium ions plus 14 water molecules. Okay, I didn't have it to do anything with this other one, so I've got 3 H2O liquid plus ethanol and that's going to give me 12 electrons plus 2 carbon dioxides plus 12 hydrogens. Okay, so this one's a little more complicated than the one we've done, the samples that we did, isn't it? So I can see, look, I have 3 H2O over here and 14. I am not going to get rid of all of these 14, but all of the 3 are going to go away on this side. So I have 11 left. 3 cancel out from side to side. The electrons go away, 12 and 12. H pluses, I have 12 here and 28 there. All these 12 are going to go away. They cancel out. But the 28, what's 28 minus 12? That's 16. So I have 16 H plus. So now everything's been canceled out from side to side. That would cancel out. And what we're left with is 16 H plus 2 dichromates plus ethanol yields 4 chromium 3 plus ions plus 2 carbon dioxide atoms, 2 carbon dioxide molecules, sorry, plus 11 water molecules. Okay, so we double check. Is everything balanced? So we've got 16 H's plus another 6, so that's 22 H's, and I have 22 H's. That's good. I have 4 chromiums. I have 4 chromiums. I have 2 times 7, 14 oxygen plus another 15 oxygen. I have 4 oxygen here and 11 here. That's 15 oxygen. I have 2 carbon and 2 carbon. And I've already done the hydrogen, so I'm all good there. Now the charge. I have a 16 plus a 4 minus plus 0. So that means a total of 12 plus. on that side. I have 4 times a plus 3, that's a 12 plus 0, plus 0, it's 12 plus and a 12 plus. It's all good. There's the equation. That's the way we balance it. All right, let's try another one. Okay, silver is sometimes found in nature as large nuggets. More often it is found mixed with other metals and their ores. In an aqueous solution containing cyanide ion is often used to extract the silver using the following reaction that occurs in basic solution. Now, there's something missing that I should have corrected here. There's something missing. You should have an OH minus aqueous at this end. I've corrected it on the one online, but I forgot to correct it here, and I will be correcting it for the next year's group, okay? So that's what we see right there. So now we need to balance this equation. Something was actually missing. Now I know something. See, Cn and Cn, there are 2 of them. It's a -1, so I don't really have to do anything with them, but I'm going to figure that out. I've got a 0. I've got a -3, which means that this guy at -1 minus 3 is a +2C. Okay, O is a 0, Ag is now a +1, N is still a -3, which means C is still a +2. And then over here I have a +1 H and a -2 O. So we see that the Cn is not that important in our reduction. We're going to have to keep it to balance it, but it's not a worrisome thing. So we have Ag going from a 0 to a +1. Yeah, Ag is the one that is oxidized. It's losing electrons. So we're going to say Ag solid plus Cn1 minus. And the only reason I'm doing that is because I have the Cn over here with the Ag. So I'm going to just keep it in there. I'm going to keep it in there. Okay, so that means it's the oxygen over here that is reducing. So O2 is going to OH minus. So those are our half reactions. Got it? Everybody good? Okay. Half reactions done. So now we have 2 O's and 1 O. Since I have an OH, I'm just going to add a 2 right there, which will balance out my O's. Okay, but now I have H's over here. So I have 2 H's that I have to account for. So I'm going to add 2 H pluses over here to balance that out. Now I'm going from a 0 charge to a 2 minus charge. That means each oxygen is gaining 2 electrons. So there are 2 oxygens, so that means a total of 4 electrons are being gained. And that means 4 electrons are extra over here than over here. So I have to put the 4 electrons on this side. Everything is now balanced. So let's go to the Ag. I've got 1 Ag, 1 Ag. The Cn's now are a problem, so I'm going to put a 2 in front of the C and the N to take care of that. I have no O's and H's, so I don't have to worry about that. Now I can go to the electrons. I have 1 Ag going to a +1 Ag. That means this side has 1 more electron. So I'm going to add 1 electron here. I see that I have 1 electron. I see that I have 4. So this guy is going to be multiplied by 4. So I'm going to take 4 Ag plus 6 Cn minus, and that is going to give me 4 Ag Cn2 minus plus 4 electrons. So the 4 electrons go away, nothing else cancels out, and we end up with 2 H plus 4 Ag solid plus 6 Cn minus aqueous plus O2 yielding 4 Ag Cn2 1 minus aqueous plus 2 OH minus. So now we need to double check. If this is the right equation and we did everything correctly, then we should have the right charges and the right numbers. So we have 2 H's, I have 2 H's. I have 4 Ag's, I have 4 Ag's. I have 6 C's, I have 4 times 2, 6 C's. I have 6 N's, I have 4 times 2, 6 N's. Then I have 2 O's, I have 2 O's. So everything is balanced by number. Let's check the charge. So I have a 2 plus 0, plus a negative 6 plus 0. Over here I have a 4 minus plus a 2 minus. So that gives me, let's see, uh-oh, something's looking a little hinky in paradise here. Oh, you know what? I forgot something. That should be 8, not 6. 8, not 6. So let's check that again. Yep, I was wrong about the C's and the N's. Sorry about that, guys. You let me just run through there. That should be 8. So 2 plus a negative 8 should be a negative 6. 4 plus a negative 2 should be a negative 6. So all's good. I just multiplied wrong. So if you look right here, when I multiplied this by 4, right, I have 4 times 2, which is 8, not 6. So easy to catch those mistakes. Easy to catch those mistakes that you make when you are kind of in a rush and hurry. Okay? So give me a few more minutes and this will be done. Hopefully you'll have done this in 2 sessions. Okay, exercise 21. This is how this applies to stoichiometry. So we have a redox titration, and the concentration of a hydrogen peroxide solution can be determined by titration against a potassium permanganate solution in acidic medium according to this equation. So I've given you an equation. We're going to actually balance that. If 36.44 milliliters of this molarity of potassium permanganate solution are required to oxidize 25 milliliters of H2O2, calculate the number of grams of H2O2 and calculate the percent by mass of H2O2, assuming that the density of the solution is 1 gram per milliliter. So let's look. So here we go, balancing. So again, we know minus 2 plus 7. Okay? Over here, it's a peroxide. Be really careful. If H is a plus 1, O is a minus 1. We have O2 gas, so that's a 0, and then the permanganate, or the manganese, is a 2 plus now. So we already know that the permanganate is the reduced part. And that leaves the oxygen going from a minus 1 to a plus 1. Yeah, that is oxidized for sure. That is oxidized. Okay, it's gaining an electron. Okay, so now we start over here again. We've seen this one twice already. So we already know where to start. We're going to start right here. The manganese are equal. So we have 4 water. 4 water means I have to add 8 hydrogen. Now that I have all of that balanced, I can see that I'm going 5 electrons. This is 5 electrons light. I put the 5 electrons over here. So now everything is good and balanced over here. So I come to this one. This one is a little bit different. So I have 2 O's and 2 O's, but I've got 2 H's not accounted for. So I have to put 2 H pluses on this side. Okay, now the electrons. I have 2 oxygens. Each oxygen is losing 1 electron, which means that I have a 2 electron differential over here. So I'm going to add 2 electrons to this equation on this side, because each oxygen is losing 1 electron, so there are 2 electrons extra over here than there are over here. I have 5 and 2, so I'm going to have to multiply this guy by 5 and this guy by 2. So I start that. 16 H plus 2 permanganate plus 10 electrons yields 2 manganese 2 plus ions plus 8 water. And yeah, it's easy to make little mistakes, which is why we always double check. So 5 H2O2 yields 10 electrons plus 5 O2 plus 10 H plus. Okay, so now we add them together. We can see the electrons are going away because they're 10 now. I see I have 10 H plus here, and I have 16 H plus here. So the 10 H plus are going to go away, leaving me with 6 H plus. Anything else? All right, good. So we have 6 H plus 2 permanganate plus 5 peroxide, yielding 2 manganese 2 plus ions plus 5 oxygen plus 8 water. Let's double check. 6 hydrogen plus another 10 hydrogen, or 16 hydrogen. I've got 16 hydrogen right there. I've got 2 manganese and 2 manganese. I've got 8 oxygen and another 10 oxygen for 18 oxygen. I have 10 here and 8 here for 18. I've already checked the hydrogen, so I'm good. So now let's look at the charge. I have a 6 plus and a 2 minus and a 0. So that is a 4 plus. Over here I have a 4 plus, plus a 0 for a 4 plus. So charges are equal, so there is my balanced equation. All right, let's go to the problem. So now I have my balanced equation. I've got it all ready to go. Everything is good. I need to do my stoichiometry. I want to calculate the number of grams. What am I given? I'm given 2 volumes, but only one of those volumes has more information, and that's the permanganate. So this volume will come back later. This 25 mils will come back later. So I'm going to start right here. I'm going to start with 0.03644 liters of the permanganate. Okay. And I'm going to go to grams of H2O2. That's what I'm looking for. So the first thing I do is 1 liter of the permanganate solution in 0.1652 moles of the permanganate solution. Okay, so now permanganate liters are gone and I have moles of permanganate. Now I'm going to use the balanced equation to go to moles of H2O2. So I know that I have 2 moles of the permanganate to 5 moles of H2O2. Moles of permanganate are now gone. And so now I'm going to grams of H2O2, and that is 34.016 grams of H2O2, and I get an answer of 0.5119 grams. So that's the answer to the number of grams of H2O2 in solution. Okay, so that's the first part of the problem, and it was exactly the same as all of the other things that we've done in class. Okay, so let's go to the second part. So the second part says, find the percent mass of H2O2 in the solution, assuming that the density of the solution is 1 gram per milliliter. What's really important about this statement is this. I'm comparing this to the 25 mils. What does that mean? If the solution is 1 gram per milliliter and I have 25 mils, it means I have 25 grams of solution. And that's pretty important because now I have 0.5119 grams of H2O2 in 25.0 grams of solution. And if I multiply that by 100, I will get the percent mass. And when I do that, I get 2.048% H2O2. And that is the answer. Okay, so little details like 1 gram per milliliter can really help us solve the problem more easily. We will be practicing this more, and we'll be working on it further. So I hope that you are going to have a good weekend. Don't try to watch all this video at once. Please try to split it up. You don't have to have it done until Wednesday. All right, bye.